My name is Klaus Wagner. I'm the Product Management Lifecycle Manager for CPROTEC 5 motor protection. And today in this second tutorial I will talk about the thermal overload protection for the rotor of the motor. There we have several functions. We will go through these functions. Then we will talk a little bit about load jam protection, an additional function. Then I have prepared a setting example, so we go through the complete settings of a typical motor and I share with you my ideas behind the selection of these settings. And finally, I would like to present a couple of additional functions and tools around CPROTEC 5 which help or which complement, let's say, the classical CPROTEC 5 device and the Dixie as such. And yeah, then I think the 2 hours are over relatively fast. Okay, let's start with a short overview about thermal overload protection for a motor. This is a repetition of the first tutorial, especially this slide. So if you want to know more details, please feel free to watch the video of the first tutorial where I explained things more in detail even. Okay, on the one hand we have the thermal overheating of the stator. This happens normally during the normal operation. Therefore we have the thermal overload protection for the stator, which I discussed in the last tutorial. So for the rotor, overheating of the rotor, here we can have different effects. One is during the start, so we consider one start, and the start can be too long, or there can be a locked rotor situation. For this we have a dedicated function called starting time supervision. Another one cares for too frequent starts, so too many starts in a certain time in a row. Therefore we have this so-called restart inhibit protection, ANSI number 66, as you see here on the screen. Then we have a problem part which is negative sequence current for the motor. Here we distinguish basically two effects. The one is loss of a phase, so one phase is completely out, the fuse is blown, then I get a relatively big negative sequence current and I need to switch off the motor relatively fast. For this we can use a classical negative sequence current protection, a definite time stage for example. For unsymmetrical voltages we have a small negative sequence current. Here we use another function called unbalanced load protection. And finally we have thermal overheating of the bearings. Here we need RTD sensors directly at the bearings, so we cannot find out an overheating by measuring the current or the voltages of the motor as such. Okay, so let's have a look for the overload protection for the rotor. This function is completely independent of the overload protection for the stator of the motor, so two different things. And we use the same, basically the same thermal model, which we see here on the right hand side. Quickly, for those who have maybe not seen the first part, I have here a power going into that system here. It looks pretty much like an electrical equivalent model, but it is for the temperatures in the motor. It's a single body model. That means I have one capacitance here, and here's one resistor, thermal resistor, where the electric power goes away. This is the heat that goes out of the motor into the surrounding, into the ambience basically. Okay, I talked a little bit more about that model in the first tutorial, so if you're interested in more details then please have a look there. Based on this model we have a differential equation here which we solve, and I will discuss now later or now how we get from this model, how we model the temperature for the rotor of the motor. We use different parameters, so the same model but different parameters, of course, because we have the rotor now which we want to protect, not the stator. And the parameters are of course based on the data we get somehow from the motor manufacturer. And here we have the number of starts with a cold motor and with a warm motor. So these are two given data entries which we normally have, together with the starting time of a motor and the starting current. So all these four belong together. That means for a certain startup scenario, this can be under nominal voltage, this can be with reduced voltage, we get the statement, okay, I can start so and so many times from cold and from the warm situation, warm state of the motor. So the number 3,2, for example, starts from cold motor, warm motor, cannot be seen separately from the second part. It belongs to a certain starting scenario. This is what we need to understand. So a starting time and the starting current. And this is very often the normal start. So you have the normal load of the motor and then, or the nominal load often, and then you get this confirmation from the motor manufacturer that this is possible with a motor. Okay, if we solve this differential equation we saw just before, we get an E function here, which we see here. Maybe just a word to these temperatures here, the theta. These are per unit values, they are normalized. So theta equals 1 means this is the maximum temperature. And we see also this temperature on the display, that means in percent. So you see a percent value if you bring this onto the relay display. And then you see if this reaches 100%, then the relay will trip. Okay, it's an E function. The theta 2 is the end temperature, theta 1 is the starting temperature, and I have here a time constant, the tau, the thermal time constant, and basically, the E function is between the starting and the end temperature. If the end temperature is higher than the starting temperature, then I have a rising E function. For example, if I switch on the motor and there's suddenly a current flowing, then the temperature will go up. And the opposite is if the motor is running and I switch it off, then the temperature will fall down with an E function. So it's kind of symmetrical here. Okay, now how can we mix everything together that we can get a model, the thermal model for the rotor? We do it in the following way. We have two information. We have the information that we can start n times from the and c times from the cold state, c like cold. And if we set this into that equation, then we come to the maximum temperature 1 if I start nc times in a row. So 3 times, for example, in a row, then I will reach this maximum temperature. From warm state, I have this equation. So I have the warm state temperature of the rotor already there. And then I can start nW, W like warm, times the motor until I reach exactly the same end temperature here. So this I can express in such an equation here. So it's just putting in the values into this basic equation here from warm state. So if we have now a closer look on that, first some explanations about theta n. So this is the warm state of the rotor. This is basically 1 over kr square. R means the rotor K factor. K factor is identical, or the meaning of this K factor is identical as I explained this for the stator ground fault protection, meaning K times IN is the current which can permanently flow into this motor, so on the stator side or on the rotor side, so that I do not overshoot the maximum temperature, basically. So the maximum current Kr time IN or K time IN for the stator here. Okay, and the end temperature basically is the starting current, if you assume this is a constant current, over KRIN to the square. So the temperature always goes somehow with the square of the current. For this relation I explained in the last webinar or tutorial. Okay, if we have now a look on these two equations here, then I have some known quantities. This is my NC and my TST, so the starting time and the number of starts from cold and warm. And I've also the starting current, so these 4 values what we have here. What is not known is the tau, the time constant for this rotor in this model, and the KR. So it's not a given value. It's a value which we need to calculate, or both are known values we need to calculate from these 2 equations. And you see we have 2 equations which are independent of each other. And I have two unknown quantities, so I can solve these two equations. And yeah, the result is what we see here on the right-hand side. Here is an approximation for the tau and an approximation for the Kr, so for this factor here. Good, that is basically, let's say, the theoretical background, what we do for the rotor temperature model. As a summary, we can state the use of this thermal model allows us to work only with a few settings, which we normally get from the motor manufacturer. Also here, the remark, this model does not describe perfectly what's going on in the motor as temperatures, simply because it's a simplified model. We could also implement a higher sophisticated model. The problem is that we don't get the data from the motor manufacturer, so we need to have somehow a practical approach to that calculation, and the practical approach is to use that data, what we see here, and use a single body model instead of a modeling, let's say, the motor with many thermal resistances and several thermal capacitances here. Okay, and as already mentioned, this is also described by the first equations. If we have NC starts with a cold motor, one after the other, then with a starting duration of TST, so this is the given data, then we will reach the maximum temperature. Theta is 1 at that point then. Here I put an example so that we get a little bit a better feeling here. I think it's a very standard example. I have 3 times start from cold and 2 times start from the warm state of the motor with a starting time of 5 seconds and a starting current of 5 times nominal current of the motor. And then we get the following data here. I get the time constant of 122 seconds. And this is a relatively short time constant. If you compare that with the time constant for the stator, there we talk about minutes, 10 minutes, 15 minutes, 20 minutes, 30 minutes, in that range more or less. And here it's just 2 minutes. That means during the motor start, where I have a high current flowing, the temperature rise of the motor is relatively fast, of the rotor is relatively fast compared to the stator of the motor. And that's also one of the reasons why the rotor is more sensitive or critical during the startup, the heating of the rotor. This is what we see here, or what we describe here with this model. Another interesting finding maybe is that the warm state here is around 1/3, so 34%, 34 point something percent. Basically, we can think about the following. If I have 3 starts from cold, then if we have a look here on this E function, this is more or less a straight, so I will have the 3 equal steps in the temperature after each start. I will get roughly 1/3 of the maximum temperature. Therefore, after 1 start, I reach the warm state, because the difference here is 1. So I will land here somewhere at 33%. Now this is not 100% linear, so therefore it's a little bit more at the beginning, and the last step is a little bit smaller than 1/3. So this is how to justify this value, or to explain this value. And it's a little bit interesting, because if we think about the temperature when we have the nominal current flowing for the stator, we are around 83% or 90%, depending on the K factor we have there. And this is much higher, so we are relatively close to the maximum temperature as regards the stator. For the rotor, we are far away, as you see. And the complete protection is done for this small part here. You see, we overshoot here the maximum temperature by a lot of a lot at the end. So here you see the end temperature is 8.6 in this example here. So this will definitely destroy the rotor if we don't trip. For example, if we have a locked rotor and we don't trip the current after some time here. Good. Then the second level here is this theta inhibit, so the inhibit temperature, or the restart limit, we can also say. If I reach that point, I can do exactly 1 more start, because it's after I reach this after the second start, then I have 1 more, and after this I reach exactly the maximum temperature. Okay, here in that case with 3 starts from cold, it's roughly 1/3, a little bit more than 66% now you see, so the gap to 1 is a little bit smaller. And you can calculate this with this equation here if you are interested. Good. Conclusion. So the rotor is very sensitive for the high currents during the startup, and we have more than one function, 3 thermal protection functions for the rotor, depending on the task or purpose what we want to do. The first one is the restart inhibit function, which is against a too often start in a row. The second one is the motor starting time supervision, the ANSI 48, which is against a too long start, so a single start which takes too long. And this can happen due to a too heavy load, or if the voltage during startup is too low. You remember maybe the first webinar when you joined that the torque is proportional to the square of the voltage. That means if I have a small voltage dip, the dip of the torque is with the square of that factor. So it decreases more at the end. Or locked rotor situation, then nothing happens and the motor will not start at all. And then I have also a certain limit after that time. Third function is a little bit the special thing. We have also an overload protection for the rotor using the same thermal model, thermal replica, as the restart inhibit function. Here we give a tripping command if the maximum temperature is reached. Theta R is 1. The difference to the restart inhibit function, however, is that the restart inhibit function blocks the closing command when the motor is switched off, because the starting part is the problem, not the motor. When the motor is running, the rotor temperature will cool down to the 33%, for example. But for the starting, I might have a problem. And therefore, this function acts or prevents a starting of the motor. Whereas this function here would also trip if, I don't know, if I have a too long start, or I start whatever is the reason with an emergency start from a higher value. And when I reach the end temperature here, not the end temperature, the maximum temperature 1, then this function will give a tripping command. This is the difference to the restart inhibit function. The restart inhibit function, one more thing maybe, assumes that I have a standard startup. The settings for this function and the temperature calculation assumes that I have regular startups, because also the motor manufacturer gives us 3 startups under certain condition, and this normally is the regular condition. So we cannot look into the future. If we reach, let's say, the restart inhibit temperature threshold, that we then understand, okay, we can wait a little bit longer to get a lower temperature, because maybe the next start is a more heavier start and will take a longer time. This we cannot do. Therefore, we assume we have regular starts with this function. Whereas the motor starting time supervision, as a difference, works for 1 start, and here we define the maximum time we can use for the starting up of a single start. Of course, this depends on each other, so there are some relationships between each other. Okay, before we go into the detail of the restart inhibit function, first some preparation, let's call it like that. The motor monitor. Motor monitor is a kind of additional functionality software which verifies in which state the motor is basically. We see it here in our tree, hierarchical tree in the Dixie. So here's the function group motor, and there's one function motor monitor, which you cannot delete because it's necessary for that function. The same with the thermal replica rotor, which we discuss in the next slides. And here we see what belongs to this motor monitor. Basically, what is interesting for us is the current flow criterion, the closure detection, and the motor state detection. Because this motor monitor evaluates if the circuit breaker is open or not, so if the motor is switched off or not, via a current flow criterion. It verifies or detects the closure of the circuit breaker. This is then when the motor is starting, basically. And it gives us information about the motor states. So is it at standstill, is it just starting, or is it running the motor? Good, and all that is part of the motor monitor here. Let's start with the current flow criterion. So this, at least the setting here, is borrowed from the function group circuit breaker. And it's a undercurrent function, as you can see here. That means if all the three currents are below that threshold, then I get here this I open signal. This indicates me that the circuit breaker is open because there is not enough current, or the current is smaller than this threshold here. This is basically the main job of this function here with this simple comparison. It's a setting in the function group circuit breaker. And then we have an add-on to that function, and this is when you switch off a fault, you could have on the secondary side of the current transformer still a current which decreases a little bit slower, and in order to speed up the breaker open detection, we have a second criterion, which is a relative criterion. This means that the current which is measured must be less than 10% of the current which was at the point of time when there was the tripping command. Now we know the tripping command, we can measure that current, and if this falls down, drops down to less than 10%, we also assume breaker is open. So this comes into the game especially after a tripping of a short circuit at the end. Good, motor state detection. We have three states: the standstill, the starting, and we come from the standstill to the starting by exceeding a threshold. It's a setting in this motor monitor function, the current threshold starting setting, which we must place somewhere between the normal operational current of the motor and the starting current. Then we have also the way back. If all three phases are open, so this is the current criterion, or if the frequency, what we measure here, is lower than a certain setting, which is below the nominal frequency of the grid, then we assume, okay, the motor cannot be starting anymore, we go back to standstill. We have the running state, and from the starting to the running state we come when the motor current decreases. So I have first the starting current, which is high, then you have the starting phase, then the current decreases, and if we see that, and decreasing means the current must be below 1.2 times nominal current of the motor. And yeah, okay, it must be not only smaller than this value, must also bigger than the current threshold open. So there must be current flowing at the end. And we want to have the nominal frequency, or a frequency which is higher than this setting, which we set below the nominal frequency. Because when the motor is running, when it is on the bus bar, then we also see here the grid frequency on the motor, in the motor current, or also in the voltage. We can come from running to standstill when all three phases are open, or if the frequency drops below, again, this threshold here. And we can also go the other way around. This is a little bit a special case. On the one hand, if the motor is running and you switch on the relay, and the relay sees then there is a current flowing, then it will go from standstill mode to running mode after a certain time. So it checks first the situation and then switches over to the running mode. And we have this path also for dynamic effects. So when we have, for example, a high-speed busbar transfer, or a certain interruption of the voltage due to problems with the in-feed, for example, then at a time when the motor is not powered anymore, it will slow down, often relatively fast, because there's a load behind the motor. When the voltage comes back, it accelerates. And in that case, we need to understand that the motor was not running all the time, for the load jam protection function we see later. And therefore we have here these frequency criterions and other criterions. So this is not fully the complete picture, it's just, I would say, see it as an orientation. Yeah, because I don't want to discuss all the dynamic effects we have here and the measures we have that we can handle them. And moreover, at the moment we are working on an enhancement of that state model. We probably will introduce another state for the motor slowdown, but this is still under development, so I don't want to talk about that now. Just have a look, and in one of the next manuals I think we will have a modification of this state model, again to handle a little bit better also some dynamic effects. Good, so that's the state model in the motor monitor. Then let's have shortly a look on the thermal replica rotor function. Also here a built-in function which you cannot delete because this is the basis, for example, for the restart inhibit function. Okay, calculates the rotor temperature of the motor, determines the state, is the rotor warm or cold, calculates the rotor restart limit of the motor, so this is the maximum temperature from which I can make again one more start, not to overshoot the rotor temperature if it's a normal start again. And it calculates the motor restart time. So this is the time if I overshoot this threshold, this restart limit temperature, until I cross that temperature again when the motor is switched off or when the motor is running. I cool down, the temperature cools down, so, and then I have a certain time until I'm back again to this temperature level. So this would be the motor restart time. And with a timer for so-called temperature equilibrium, during which the motor is not allowed to start. I think I talk about that a little bit later when we have some diagrams about that. So here we have the logic diagram. First of all, I can define if I want to storage the thermal replica, if there is no auxiliary voltage, so if there's a power supply failure of the relay, then maybe I want to start again with the already existing temperature, and I think it's a good idea to switch that on. Then I have the settings we discussed already, the starting current and the starting time, for which the number of cold and warm starts apply according to the motor data, what we get from the motor manufacturer. Then I will have here, or I have here, a restart limit. That means this temperature is exceeded. So it's like, no, it's not a warning. This is really the signal which I can use to block the closing command of the circuit breaker. And this is the calculated rotor temperature, which comes out here of this calculation, represented by this box here, more or less, white box. Okay, out of this white box also comes the motor state, is it warm or cold, according to a setting what we have, and I come back to that setting later, how we can set this setting. Then this equilibrium time, which becomes active all the time when we switch off the motor. It's a setting which we can set. The factory setting is 1 minute. That means that after I've switched off the motor, I wait at least for that time until I can restart the motor again. The idea is that the various temperatures in the rotor have time to balance out a little bit, because we don't have an equal distribution of the temperature with different temperature levels, and it's just, let's say, a basic time to wait until we restart the motor again, so not to have overheating of the rotor. Then we have two factors which are multiplied with the calculated time constant for the rotors. You remember in the example before we had this 122 seconds, and I have two factors. The one is here for the cooling down effect when the motor is running. So this we can consider kind of additional safety factor to say, okay, the motor temperature rises relatively fast, and when then the motor is running, then it cools down, but I make a certain delay in the cooling down time here. And I have a second factor here. This is the factor if the motor is at standstill, then I probably have a longer time constant, a longer process to cool down the motor, because the ventilation is missing. If the ventilation is missing, if not, if I have a independent ventilation, let's say, even if the rotor is at standstill, then I might use the same, so the factor 1, the same time constant here for the cooling down, because then the airflow or the power which goes away, the temperature which goes away out of the motor is equivalent with the same, more or less. Okay, so let's have a look on this motor restart function now finally. I already mentioned this prevents from restarting the motor if the rotor would exceed the permissible thermal limit due to the starting, and this is a thermal stage. On top of that, we have a counter stage. The counter stage prevents from multiple starts and stops in a short time interval. So sometimes you get additional data from the motor manufacturer saying the motor can be started so and so many times in a certain time period, 2 times in 1 hour or something like that. So, and if you have such a data from the motor manufacturer, you can use this counter stage to describe this data. And finally, we have a timer stage. This is for, let's say, if you get a statement from in the motor data that you should have a certain time between 2 successive starts of the motor. So a time in between 2 starts. So this is a little bit different to the counter. Different approaches of data, and we can use, or you can use then these stages, whatever data you have. Of course, I would consider this here the most precise one because we do there the calculation for the temperature. And here we have just a counter and a timer, so a relatively simple function at the end. Okay, this is the function as such. This function prevents a close command with a signal restart inhibit, which would bring the rotor to a too high temperature. And I have these 3 stages here. You see the thermal stage is always active. The counter and the time stage, they are as an option. Therefore, they are gray. You can activate them at these stages. I think I forgot one point in this diagram here. No, it's on the next, I think on the next page. No, it's not coming. Okay. Then we have to discuss this separately. This is now, let's say, again, our classical 3 starts from cold. And here we see different curves, the red one and the blue one. The red one has a higher temperature, and this is the temperature in the upper bar, or the upper bar side, and the blue one is on the lower bar side of the rotor. So if you think about the cage here, indicating that we don't have just one temperature, it's a temperature distribution somehow in this rotor. Again, we don't get precise data, and it's probably not necessary to have that because the motor manufacturer just certifies or declares, okay, with that number of starts in a certain time, or certain time and a certain starting time and starting current, everything is fine. So it's a very rough information, and based on this rough information we define our model. Therefore we make, of course, a simplification, and we use here the black curve basically. That means after the 3 stages with our calculation we are also at the maximum temperature, like maybe the maximum temperature of the upper side of the rotor bar or the lower side of the rotor bar. So in fact, we could have here 2 different maximum temperatures as absolute values, but as relative values they will be identical because we have the data, 3 starts from cold, 2 starts from warm. So there's no difference for us what is going on inside in the rotor as such. Okay, so here is an example. I have here, let's have a look on these 2 diagrams. Here I have the time, and here I have the current in the motor, and here it's the temperature in the upper diagram. And here we watch just 2 signals, the restart inhibit and the warning signal. You have the motor start, then the motor is continues to run here with a nominal current, and then it's switched off, and then I have this cycle 3 times here, and at the end it's switched off. Okay, when I switch off the motor, then this restart inhibit timer, or this restart inhibit signal, becomes active, and this is this so-called equilibrium time. That means it's the time where everything is at hold, at standstill. So on the one hand, the temperature calculation we do internally. On the other hand, during that time no restart is possible because we issue this signal here, which can be used for the restart. Also here, interesting is then this point here, when we cross now this calculated restart limit, then the warning signal comes, and this is active as long as we are above this restart limit. So this is the indication that we are above that calculated limit temperature, so we must not restart the motor. The restart inhibit signal, on the other hand, again starts when the motor is stopped only, so at standstill. So the state standstill of the motor is the trigger that here, come back please, that we start here, or that we give this restart inhibit signal. And this restart inhibit signal lasts as long as I'm above that temperature and the motor is at standstill. So since this blocks the starting, this will remain here until the temperature goes down. And you see here we have a second time, a minimum restart inhibit time. This is just, let's say, a minimum time you can set. So the longer one wins at the end, how long this restart inhibit signal is given. Maybe one word, we have one setting, it's called the automatic restart inhibit function, yes or no. This means if you set this to yes, then this restart inhibit signal is connected with the internal close command of the relay. That means you cannot give this close command to the circuit breaker, this will be blocked. And additionally, the tripping command for that circuit breaker will be activated for the complete time, which is not a problem because the motor anyhow is at standstill, the circuit breaker is open. Both prevent a reclosing or a closing of the circuit breaker during that time. If you don't want this internal coupling, then you need to switch the setting to no. Then you have just this signal restart inhibit, and then you have to work with that signal and make an external wiring to block the close command. Good. Here are some examples how this works under different conditions. Here I have 3 times a start in a row, and then the motor is running here for a longer period. And then I switch off the motor, and then here the temperature cools down further. And we see here, every time we switch off the motor, then I have this equilibrium time, so the time to balance out the temperatures in the motor, so give the motor a kind of rest, so that we can restart again. Here I have this black part. This is the warning signal again, which is active as soon as I cross this restart limit temperature here. And the blue one is now my restart limit or restart inhibit time. And this is active as long as I'm above that threshold here, or in that case, here you see the minimum restart timer, inhibit timer is longer than this small time here. So then this minimum timer wins, and I get this blocking signal, the restart inhibit signal, for the minimum time here of this timer. Yeah, and here it's another example. Here I have, as a difference, the motor here is running longer than the temperature needs to go under our threshold here, under our limit. So here the warning will be active, and when I switch off the motor here, then it's switched off when this restart limit temperature is already undershoot. So there will be no extended blocking of the closing command. We just have here again this equilibrium time. This is a setting which is standard as a standard set to 1 minute. You have also the choice to set this to 0 if you don't want this behavior, this always, let's say, short blocking of the closing. Here I let the motor run until here, and then I switch it off. So here then this restart inhibit signal comes over the complete time, and in that case I have a relatively slow cooling down. So here the calculated restart inhibit time wins. So the minimum time is much smaller, so this signal is maintained until I cross here the restart limit temperature again. And here finally I have an example where I go beyond or below that limit here while the motor is running. Then here, as long as the motor is running, we don't have any of these restart inhibit signals. I have just the warning, and if I switch off the motor here, I will get just 1 minute or this equilibrium time as a blocking signal, and then I can continue. Okay, so I hope with these examples it's a little bit more tangible, more clear what this function does. So let's go to the second stage, the counter stage. As already mentioned, the counter stage allows a certain number of starts in a certain time period. And if the maximum number of starts have taken place, a restart inhibit signal is issued until to the end of this time period. I put here an example. Let's assume I have 60 minutes and in this 1 hour, 60 minutes, 2 starts are allowed. Let's start first at 0 minutes and stop after 10 minutes, and then let's have a second start after 17 minutes and stop after 33 minutes. So what happens? After the second stop, there must be a blocking signal because the 2 starts are already there, have been done, have been performed, but the 60 minutes are not yet over. So therefore the inhibit time is 60 minutes minus the 33 minutes. So after this shutdown of the motor, I will have 27 minutes of this restart inhibit timer here, which will block another startup. Maybe I did not mention that. I have always the possibility of an emergency start or restart via a binary input. So if thermically I would not be allowed to start because it endangers the rotor, but if from the process point of view I need to restart a motor because something else more severe happens, then I can override all that stuff, and with a binary input then I can of course restart the motor nevertheless. So this option is always there for all of these thermal functions. Here's an example, or our example. Here's the motor running. 2 times it's switched on and here it's switched off, and with the second shutdown of the motor this restart inhibit signal is activated and it runs until the end of this time interval. So this would be our 60 minutes here, and this is just the difference, and then here I have a new cycle, a new story begins. Okay, let's shortly have a look on the timer stage. The timer stage allows the restart of the motor only if the time span between the restart and the last start, or the first start and the second start, maybe better, is bigger than a certain setting, minimum time between the starts. If the motor is switched off and the time after the last start is shorter than this setting, the restart inhibit signal will be active and you cannot restart the motor. Sounds a little bit complicated. We see immediately a diagram. I think then it's clear. It's a relatively simple thing here. I put also here an example. I have a minimum time between the starts of 25 minutes. I start the first time the motor at 0 minutes and stop it after 12 minutes. And the second start is at 30 minutes and stop at 80 minutes here. Good, then I have this inhibit time, and it's the minimum time between the starts, the 25 minutes. And I subtract the 12 minutes because this is the point of time when the first start is over. And then I have 13 minutes left until the 25 minutes have elapsed, and then I can make the next start of the motor. This is what we see here. So here the motor is started, motor is running, and then I start this restart inhibit timer with the starting of the motor, and then I have the 25 minutes between the starts. So when I switch off the motor, the restart inhibit signal comes for this 13 minutes until this restart inhibit timer has elapsed, and then everything resets and I can make more starts or new starts here. Okay, again, this timer and counter stage is if you have additional data from the motor manufacturer that goes into that direction, then you can apply these stages, activate these stages. It's an additional help. I would say in addition to the thermal stage, if you have the data for the thermal stage. Okay, this is the recommendation. You can do what you want. You don't need to use one of these functions or a special of these functions, one special of these functions. It's up to you at the end. So what we can do is to offer all these principles here. Good. Maybe last point, the thermal overload protection of the rotor as a protection function. So this function issues an operate signal, a trip signal, if the calculated rotor temperature reaches exactly the 100%, as a difference to the restart inhibit function, which just blocks the closing command if we come to a level where the next start would exceed the maximum temperature here. I can use this stage also optionally only as a warning, because there's one, it's good because it's very precise. Yeah? You never go over the 100%. On the other hand, if your process maybe is more important than a couple of percent of the rotor temperature, then you would maybe trip with this function at the end of a restart, and this would be maybe not desired. So it depends on the application here. Yeah, it's a very simple thing. I have here the rotor temperature coming from our thermal replica, which we discussed before. Then I have this threshold 100%, and then if we exceed this 100%, then at the end I will give here a operate signal, and yeah, that's it. I will trip then the circuit breaker. I can use the option only warning. That means here operate and fault record is blocked. Yes, then I will block that part here, so there will be not a fault record and no operate signal. I will then get the warning signal when I exceed here this threshold at the end.